Hello, welcome. We don't have an MC at the moment, so I'll just mention if you need the bathroom keys, they're over by the mixer. And I'm going to talk this morning about basement MEMS. I think it turns out if you put basement in the title of your talk, you end up down here. So thank you for finding it. What I meant by basement was, I was very inspired by the sort of garage biotech folks' ethic and approach to life of buying up old surplus industrial equipment and trying to do cool things with it that are maybe what the manufacturer intended and maybe not quite. And I wanted to apply that to making small parts out of silicon. So what I came up with was this basement MEMS setup. It's still very much a work in process, but it gives an opportunity to talk about lasers, kilowatt radio transmitters, dangerous chemicals, racks of compressed gases, and turbomolecular vacuum pumps, and really I think the best opportunity I've found thus far in my life to build up my collection of esoteric plumbing fittings. So I'm going to talk mostly about the processes and equipment, because probably most of you don't want to make exactly the same stuff that I want to make. That's one reason. The other reason is this is still, as I said, a work in process, and I haven't, frankly, made that many successful things. So I think it's going to be interesting to talk about how this stuff is made, what kind of stuff you need to do it, and what the processes look like. So I think all good projects start with some kind of weird obsession. For me, it's mechanical watches. I really have been spending a few years trying to figure out how to make all of the parts. One of the more interesting, I think, advances in the field in the last few years is making parts out of silicon. And it has some advantages. It's completely anti-magnetic. It has some cool physical properties, and you can make really any geometry you can think of, kind of in the same way you can make things out of 3D printing, but backwards, because you're removing stuff a very small amount at a time. And so traditional mechanical watch, this is kind of the heart of it. You've got a balance wheel, a hairspring, a pallet fork, and a escape wheel. And this moves back and forth. And what a mechanical watch does is it counts how many times it moves back and forth. And this is a very traditional design. They've been made this way since late 1600s. This is a more modern design made out of silicon. And this is just a hairspring made out of silicon. So I want to sort of get into that space, be able to play with those kinds of parts, shapes, ideas. I'm not so much trying to make transistors. A lot of the tools, techniques, processes I'll be talking about can be applied to that, and I'll have some links at the end to people who are doing that and applying this kind of stuff toward making more electronics-oriented things. And so we'll get to that. So the starting point is, how do you go from a silicon wafer to a finished part? And the process is you design your part, you get some silicon wafers, you put down a pattern on the wafer that represents either what you want to make or the opposite of what you want to make, the negative image of it. You etch away the stuff that you don't want, and then you have to do some post-processing to cut out the parts and attach wires if you're attaching wires. So this is good for making small physical components, gears, watch parts, pressure sensors, that kind of stuff. Also good for making semiconductors if you sort of repeat some of those steps a few times. So rather than doing one layer, you're building up multiple layers with different materials. The tools and processes can also be used for making things for microfluidics, for plasma nitriding if you want to get that cool gold color on your cutting tools, for vacuum heat treating, for all kinds of other kinds of geeky things that can be a good part of your project. Okay, so the first step is lithography. You start out with your substrate, your silicon wafer, your quartz wafer, whatever you're using. You put a layer of stuff on top of it, and that's called the resist, usually a photoresist, a photosensitive resist. And much like developing film in a dark room, you expose it to light, but you filter some of that light through a mask. So the light doesn't hit the entire photosensitive substrate, it just hits some parts of it. You develop it, and then the etching process will etch away material below the parts that you've left. So you make a mask that exposes the parts that you want to etch away. You then use various processes that can be a wet chemical process or a dry etching process. We'll get into a little bit of that. to get rid of the parts that you don't want. Once you've finished that, in my case, I'm pretty much done. I've got the part that I want. For a lot of other processes, you might then lay down a layer of metal over the top, use a different mask, and start again. Okay, so the simplest way to do this that I've found, and I should mention I'm completely an amateur at this. I do professional engineering in completely different areas, but this is very much a hobby project. So this is something I'm playing around with. If any of you happen to be experts in the areas, please jump up and let me know better ways to do things. But the absolute easiest way that I found to do this is there are film photoresists that you can get. They are a layer of the chemical photoresist sandwiched between two plastic layers. You peel off the bottom plastic, you stick it down to whatever you want to etch, you bake it on a hot plate, you peel off the top layer, you expose it through your mask, then you peel off the top layer and you're good to go. There's much more complicated ways of laying down a layer of photoresist, I'll talk about in a second, and there are much more complicated ways of exposing it. This is, as I said, the simple way. So the mask that you can kind of see there, this is an exposure gauge. So I'm just trying out this little box that I built for exposing. It's a 3-watt UV LED in a little foam core and gaff tape box to hold it about the right distance above the thing. It's not perfectly collimated by any means. You're not going to be making, Intel processor, not even a 404 on this thing. But for starting out, for trying things out, you don't need anything more than this, a source of UV light and a place to put it. The exposure gauge, it gives you a way of telling how exposed the resist is. You want to get it just right so that the exposed parts stay stuck on and hard enough to resist your chemicals, and the other parts get washed away so that the substrate is exposed. So here are two exposures, one's 30 seconds, one's 60 seconds, and you can see kind of the difference. And you want it to end kind of in the middle there. I'm using a really simple timer here. I really like using Arduinos for most things, but frankly, it was cheaper to use the surplus little timer than to buy an Arduino relay and set it up. One of the recurring themes here is going to be trying to reuse and do things as inexpensively as possible. So if you don't want to use the film photoresist, either because there's only a couple of different formulations available of it, they aren't suitable for all chemical processes you might want to do, you can get all kinds of liquid photoresists. And you can make your own, you can buy very expensive bottles of it. Most of the commercial suppliers are going to give you a quote like $300 to $500 for a couple hundred milliliters and tell you to store it at negative 20 degrees Celsius and use it within 3 months. I'm not going to do that. There's much simpler ways of making it that you can find out if you use your favorite search engine. They work pretty well for a lot of chemistries. Another kind of recurring theme is that the processes that I'm using come from semiconductor manufacturing. Moore's law tells us that semiconductor manufacturing advances really rapidly. The hardware, the techniques, the processes change pretty often. And so there's a huge secondary market of old equipment, most of which is really high quality, is really actually fun to work with because it was designed and built to be repaired, maintained, to be very high reliability in ways that most consumer electronics just aren't. And so a lot of what I've tried to do is sort of take and adaptively reuse that. So here's a commercial spin coater. What this does is when you're using a liquid photoresist, you take your substrate, which is usually roughly circular with one flat edge, you spin it really fast, you drop a drop of liquid in the middle, and it just kind of flattens out. And by controlling the speed that you spin it, the acceleration and deceleration, and the amount of liquid you drop, you can control the thickness of the resist layer. These are still pretty expensive, but are available used. I'm building my own using I've got a couple versions. One is using a surplus spindle motor out of a commercial machine. The other is using just a couple bearings and a design from a bunch of woodworkers who are building vacuum chucks. And it works well enough for my purposes. This one, it's a two-phase AC motor, because I don't know, that's what they had in 1975 when they were building it. The best way that I found to control that is actually a stepper motor driver running in micro-stepping mode, which has two phases and tries to approximate a sine wave in micro-stepping, and it works well enough, and it spins the motor at the speeds I need, accelerates, deaccelerates well. And then to drop the liquid photopolymer on, there's an open source 3D printable syringe pump, which works very well to hold a 1 milliliter syringe and just drop a precisely controlled amount at the right time. Okay, so you've got your substrate, you've got a layer of something on it for a mask. Now you need to put a design on it. You can either do that using this kind of setup. The absolute simplest, you're doing this with very few resources. You can literally print it out with a laser printer on transparency film. You can get decent resolution, good enough to make simple transistors and stuff anyway. And you just lay it on top, printed side down, and expose through that. If you want to get more complicated, probably the easiest thing to do, or the best thing to do, is set up a maskless lithography setup. So rather than using a mask at all, you get rid of that completely and use a laser to write directly on your substrate, write directly on the wafer. So you need a UV laser. You shoot that through a beam expander, because your optics down here are going to work better with a fatter beam. Put it through mirrors that steer in X and Y, and put it through a lens that then will map onto sort of a two-dimensional plane. It's called an F-theta lens. They're not that readily available surplus, but do show up. There are some inexpensive Chinese manufacturers on Alibaba that work pretty well, and write directly on your wafer. To drive this, so these mirrors are driven by galvanometer motors that look something like that. These are giant, ancient ones. These are out of a microscope setup. Probably the best commercial equivalent right now for hobbyists is to look into inexpensive laser light show projectors, which have a similar kind of XY mirror setup and have more open interfaces and better ways to drive them. But I'm driving this now through ultimately with Linux CNC. So you draw your pattern, you tell it to write, you use the spindle on and off commands that you would use for a CNC machine to turn the laser on and off, and you go around and you draw your pattern directly on. Once you've got the pattern written on your mask, you then need to etch away the silicon. And this is where we start to get into some of the more industrial processes and equipment. There's two basic ways of etching. If you use a chemical etch with silicon, you end up with something like this, which is called an isotropic etch. You don't get straight lines up and down because the chemical's kind of attacking from the sides, and the silicon crystal is oriented in such a way that you end up with, depending on the exact kind of silicon, usually around a 55-degree angle, slopes to your edges. So you end up with something that looks like that. That works for some parts. It tends to work well, like for microfluidics, where you want to run a liquid through the channels. But for the parts I want to make, I want square edges. So I need an isotropic etch, which means that wet etching isn't going to work very well for what I want to do. But it's the easier setup. It works well for some things. We'll talk a little bit about it. So to do a wet etch, you take your silicon wafer with the mask on it, and you drop it into a chemical like KOH, potassium hydroxide. It's a strong base. You probably see it in things like Drano, and it will selectively etch away the silicon while not eating away the mask as quickly. If you want to make, if you're trying to cut out three-dimensional pieces, you're probably not going to be able to etch all the way through your wafer to cut a piece free. But again, for etching channels, if for making microelectronics, it works really well. And you can do it just with a container of KOH on a hot plate. You just leave it in there. You get like maybe a micrometer per minute. So it's not a fast process. But again, if you're only trying to etch 50 or 100 micrometers, it's not that bad. To do anisotropic, to get straight edges to your parts, it gets more complicated. And the process that I've really dug into is plasma etching. One of the original versions of this is called deep reactive ion etching, was patented by Bosch more than 21 years ago, and involves putting your wafer into a plasma chamber with the right composition of gases, that you get ions that will attack the silicon and accelerating those ions down toward your substrate so that they hit both the masked and the unmasked parts, but selectively etch away the silicon that hasn't been masked. To get really nice square edges to your parts, the ions that you're bombarding this thing with are not going to be coming down in a perfectly straight line. Some of them are going to be bouncing around to the sides. And so they're going to hit the sides of your channels as well as the bottom. They're mostly going to hit the bottom, but some of them are going to hit the sides. And so you alternate. You do a round of bombarding with chemicals that are going to etch the silicon, and then you actually bombard it with a little bit more mask. You apply a very thin, not very strong layer of a mask to the entire thing, and that's going to coat the sides of the channels, it gets the bottom, it goes over the top, it kind of goes everywhere. But that gets eaten away on the bottom of your channel very quickly when you start to etch again. It's not very strong, but it's strong enough to mostly resist the few ions that are hitting the sides. And so by alternating masking, bombarding, you eat away at the bottom of your channels but keep the sides protected. To do this, you need a chamber, a plasma chamber. I'm using an RF inductively coupled plasma, and we'll get into that in a moment. You need an RF source, so this is going to be a few hundred watts to a kilowatt of usually 13.56 megahertz, the ISM band, so you're not interfering with local TV too much. That gets sent into your chamber through a matching network, like an antenna tuner. There's a smaller RF source that connects to the chuck so that the ions that you're creating want to go and hit your chuck, which holds your wafer. You need a whole vacuum system, because all of this has to be done under a pretty good vacuum. And then you need to introduce the right gases in the right proportions at the right time into your chamber. So you do that using mass flow controllers. I've got a slide later about mass flow controllers, but if you've ever tried to build a system where you're precisely controlling a flow of gas for anything, they're awesome. They're really nice. Somebody has just taken the whole system, put it into a nice little box, and you just buy it and plug it in and use it. Okay, so my inspiration for this part was MIT's 1-inch fab project. That's a project that's trying to build a whole semiconductor processing line using a 1-inch substrate. Most commercial systems are now on to 8-inch or bigger. They're trying to build a whole system for under $1 million. And as one piece, it includes a deep reactive ion etcher, which is covered by this 2014 master's thesis by Gould and Singh. And I owe a great debt to them for documenting the whole thing really well. It's been great to read through steel pieces from and try to reuse. I share the goal of trying to build a whole system for less than $1 million. But I'm really trying to keep it down. I'm not sure if my partner's in the room. Anyway, I'm trying to keep it down under the cost of, say, a decent gaming PC. Fortunately, the cost of GPU cards keeps increasing quickly enough that with that as the metric, it's easier to keep. Okay, so the plasma etching setup, and on the right is my basement. So this is the setup down there now. On the left here, we've got a plasma etching setup. So here we've got the chamber where you're making the plasma. So this is coupled to your larger RF source. There's a coil that goes around there. It's inductively coupled, and so it creates a plasma out of these gases that you're letting in through the top. The ions all shoot down, they're attracted to the chuck, they hit your chuck, whatever chemical reaction happens, and the products, whatever gases you're creating, go out through your vacuum system. Okay, so you need to create a vacuum. There's a bunch of ways to do this. This is sort of the easiest that I've found thus far, is to use a turbomolecular vacuum pump. I've got a slide that shows that a little better in a little bit. But you need a high vacuum pump. This will get you down to pressures of 10 to the minus 6, 10 to the minus 7th torr. Somewhere between the vacuum, if you open the door in the space station, and the vacuum on the surface of the moon. Probably better than the surface of Mars. I want to build a Mars box, by the way. Maybe that's next time. So it gets you really a pretty good vacuum. It's down far enough that you have to start worrying about, the main source of pressure inside this thing is water vapor that's gotten bound up in the stainless steel surface of the interior of all your parts. And that sort of slowly creeps back out, and that's most of what's inside this when it's running. There's a conductance valve here because we don't actually want the chamber to be at that low of a vacuum. We want maybe 10 to the minus 3rd torr, a few millitorr. So there's a conductance valve here, which is in this case, it's just a big flapper. And when it's horizontal, it stops molecules from bouncing out. When it's vertical, they pass through more easily, and so the pressure in the chamber drops. And then there's a gate here, because the gate valve is just like an on or off, can allow gas to go through or don't. And that's used to separate off the plasma chamber from the rest of the system, so they can leave this pumped down or purged with dry nitrogen to keep water vapor from getting in, because it's humid, because it's my basement. The high vacuum pump will only work if it's already in a vacuum. It has some vanes that spin really, really quickly. We'll get to that. I've got some pictures. So it already needs to be in a vacuum. So you need a backing pump. And this is, if you think of a vacuum pump, you might think of like a box about that big that makes a whirring noise, and it looks a lot like an air compressor, works a lot like an air compressor. And that's pretty much what's down here. There are different kinds, there are different styles. You can fill them with different kinds of oil, and that matters based on what you're trying to do with your chamber. We won't get into that. Okay, so here's sort of another view with a few more parts. So here's the turbo pump. There's the 4-line trap, because the backing pump will release a little bit of oil, and so you want to trap that before it gets into the rest of your system. There's a couple of pressure gauges. If you start working with vacuum, you quickly realize there are a ton of different kinds of pressure gauges. They tend to work at different pressure ranges. Bad things happen if you turn some of them on when they aren't at a good enough vacuum. And so you end up having a bunch of them hung off the system. I also just mentioned that like half of the stuff in this stack is there, these little funnel-shaped pieces of this chunk. Like half of that stuff is just there because I'm buying pieces as cheaply as I can find them from different sources, and then having to bodge together adapters to like plug everything together. So this is the source of the comment about your box of plumbing parts. A surprising amount of this, and frankly most other science I've been involved in, sort of devolves down to plumbing. So the gauge up here above the gate valve is good for measuring higher pressures. So down to 10 to the third, 10 to the minus third, 10 to the minus 4th torr. The cold cathode gauge down here is the cheapest gauge I could find that goes down much lower, so that I can tell how well the turbo pump is actually working. Okay, there's my pump picture. So the pump is in here. Wait, I'm looking from the side. It's in here. If you picture a jet engine, that's pretty much it. It's electrically driven. It has a bunch of rotors that look like what you can see there. This is a particularly dirty turbo pump. I don't know if you can see that in the picture, but one of the challenges with buying surplus is always trying to figure out what this stuff was used for in the past and how to clean it. I think in my last slide I mentioned it's really good to have a plan for how you're going to clean and dispose of things as you're working on it, because if you're buying industrial surplus, you never quite know what it's been used for. So you kind of want to take it out of the box with gloves on and just assume it's bad. So your turbo pump, you've got a bunch of rotating vanes. In between those rotating vanes are fixed blades, and it works kind of like a ping pong machine. So gas molecules, this is looking down the face of it. Gas molecules come meandering down there just through Brownian motion or like bouncing around in classic Newtonian physics and stumble their way into these rotating blades and just get bounced down. And just by virtue of the molecules bouncing around inside this chamber and eventually making their way down to the pump where they get batted down further, eventually they mostly go out of the chamber. It spins at, I think, about 90,000 RPM. Mine are old, so they're not quite there, but the noise that the sound that it makes as it spins up is amazing, and it's kind of my favorite part of the whole thing. If you remember the old, the good Batman, the seatbelts fastened, turbines to speed, that's kind of the theme here. Anyway, so they're driven by electrically. You've got a motor controller here. It's basically a 3 or more phase motor. So it starts out at a low frequency, ramps up, and runs the whole thing up to speed. The electronics aren't that complicated. There's some pretty good plans online, like for older Edwards pumps for doing DIY controllers. And that's probably the least expensive way of getting into a turbo pump. The way that I did it was to find some cheap old ones, buy a few of them, and in as-is condition, and just try out and mix and match and try to clean them up and get them working. It's not the fastest way to do things. You're probably better off finding one that they say works, that has documentation, that has a DIY controller, and building the controller yourself. If you want to know what's happening in the chamber, then there's something called a residual gas analyzer. So this is a small quadrupole mass spectrometer that sits in the bottom of the chamber, connects to some software that I got on 3 floppy disks. The documentation says that it works well under Windows NT, but that they really recommend Windows 3.1. I've had pretty good luck with Windows 98 with it, but I haven't networked that computer. It's a standalone. But when you run it, you get a little, I don't know if you can see the little graph, but here's the atomic mass starting from 0, I think running up to about 200, and it tells you how much it's measuring at each of those masses. And then there's some software that will analyze that and tell you, yeah, you've got water vapor in your system, and how much the partial pressure of that is. And so this is really useful for telling what's going on in your system. How badly are things contaminated? Is the whole thing full of pump that's backed out of your backing pump? I'm sorry, full of oil that's backed out of your backing pump, or is it reasonably clean? For control, this may sound like a joke, but I mean it very seriously. I took a lot of inspiration from model railway control systems. If you've ever seen one of these huge layouts, they often have little control panels with lots of switches, nice little pieces of tape, like laying out what's happening and which switch is moving like which piece of the thing. And so I like to think this is my own small tribute to the long history of model railway connecting to hacking. But anyway, we've got a basic switch panel here to turn things on and off. At this point, I mostly rely on myself to not turn the wrong thing on at the wrong time, which isn't the safest way of doing things, but is quick and easy for prototyping. Things like there's the high voltage for the cold cathode gauge. If you turn that on when the system is at atmospheric pressure, you'll burn out the gauge. It's dead. If you open the gate valve and vent the system suddenly to atmosphere, there will be a loud bang. So you don't want to do that. So that's that control panel. These are another pressure gauge, the controller for that conductance valve. So this connects to one of the pressure gauges. It has a bunch of settings, and it's got a little PID loop controller to control the position of that flapper valve to keep the right pressure in the chamber. The residual gas analyzer, and then the old Pentium, I think it's a Pentium 2 actually, computer that's running Windows 98. My day job is working in medical stuff, so I'm used to having to keep old computers running. For the Chuck RF source, I was really happy to be able to grab a relatively new open design for an RF amplifier. So this comes out of the Taper group. They built this as part of their open software-defined radio project, and it's a broadband 20-watt amp. I only need like 10 or 15 watts, so it's kind of perfect. It's available as a kit. It's the first thing I built that was a kit entirely built out of surface mount components. It's easy to build, it's fun. If you need a 20-watt amp, I highly recommend it. And so there it is running with a little test source at 13.56 megahertz. For the main source, you need something bigger. And so this is a surplus 1 kilowatt RF source. The industry for plasma etching sort of standardized on 13.56 as part of the ISM band, probably mostly in the late 80s, early 90s. If you're looking around, you'll find a lot of kilohertz kind of sources, I think 100, 150 kilohertz kind of range that were used before that, and they're still used for some things. But the 13.56 megahertz are a little easier to work with, a little easier to find. This thing is still water cooled, so you have to have a water pump, a pump of stuff. Another recurring theme is that there's a lot of infrastructure around getting this running. You know, just to get the valves working, you need an air compressor, you need regulators, you need solenoid valves to turn on and off the right air lines at the right time. Similarly, to get the RF source to turn on, there has to be water running through it. And it has a flow sensor and will shut off if there's not sufficient water. It also has an interlock where if it's not connected to a control system, it won't turn on. And this is good to know when you go shopping, because you'll find a lot of folks who list these on eBay, on other sites, and say, well, I turn it on, the power light comes on, but nothing works. And this is often because it has safety interlocks. And so on this particular one, there's a 25 pin, a DB25 port on the back. It expects a couple of those pins to be shorted together, and it's a safety thing. If you connect that to your chain of interlocks, if it's open, then the RF source knows to shut down. And so a lot of these end up getting listed and sold for not much money as is condition or not working, when actually it is working fine and it's just the interlock. So hot tip, if you're shopping for surplus RF sources, look for ones that turn on but nothing happens. These are intended to work into a 50 ohm load. Just like ham radio or other kinds of radio sources, they're intended to work into a 50 ohm load. The chamber that we're coupling this to is almost certainly not a 50 ohm load in any way. And so we need something to match those. The easiest way to do that I've found is to use an antenna tuner. This is a Heathkit ham antenna tuner. And you sit there and you turn the knobs, and it's, for those of you who are into such things, it's a pi network. You've got a couple of capacitors, you've got an inductor in the middle, and by varying these, you can adjust the characteristics to match both the resistance and reactance of the chamber to the RF source, get a smooth transfer of power, and avoid having your RF source going to shut down because it's getting too much power reflected back. You can either do that manually, or what I'm building is a servo drive to do that. Because when you're doing the Bosch process, deep reactive ion etching, remember you're bombarding with ions that are etching away the silicon, and then you're putting that mask layer back on. And you're switching that maybe every couple of seconds. So you're not going to be able to do that by turning the knobs by hand, but you can do it by turning the knobs with motors. So this was my first effort. So these are a couple of air variable capacitors. There's fixed pieces, and then there's parts that move, and depending on how you move it, the capacitance changes. These are some motors that are attached to it with little drive sprockets. This is mostly out of an old commercial product that I bought. And when I bought it, I got one that was too new. It ends up being very tightly packed together, very optimized, I'm sure very efficient, and a nice small form factor for when it was eventually installed. But by going back another 10 years, I got one that is much more open, more designed to be worked on. And so the case all comes nicely apart. You've got some pancake gear motors there, coupled with nice big vacuum capacitors. And by turning those, you vary the capacitance. There's also, not shown in this, a roller inductor, which is a long coil of metal with a little finger that follows along it. You spin that with a motor. And by varying these, you can, again, adjust the capacitance, adjust the inductance, and by measuring the amount of power that's going forward in your system, the amount that's being reflected back to the transmitter, you can tune things so that you get an efficient transfer of power between the RF source and the chamber. I'm driving all this with one of these Adafruit motor controllers, which are a great little product for controlling motors from Arduinos. Work really well and handle the power that I need without any problems. Let's see. Another process I want to talk about, there's a couple more processes I want to talk about a little bit, and then I'll get into some of the other links, other kinds of things that you can do. One is sputtering. So sputtering is taking your source, your sputtering target as it's called, which is the metal that you're going to be using to coat your substrate, putting it into a plasma and getting some of the atoms of your target to ionize and get shot onto your substrate. So it's often used, and the sputter coater that I have is meant for coating targets for electron microscopy. So if you have an electron microscope and you want to look at something, it has to be conductive. So if you want to look at an ant, you need to make that ant conductive. And so this is from Wikipedia. It's a picture of an ant that's been gold coated. And you often use gold, or gold, platinum, silver in some cases, titanium. You know, all these metals can be sputtered onto targets, and that's commonly done for electron microscopy. It's also done for things like if you want to put a thin metal coat onto a plastic disc to make a CD-ROM, you could sputter it on. If you want to gold coat or platinum coat a 5 1/4 floppy to give out to the game of the year, you could sputter it on. Sputter coater has a vacuum chamber here. There's that blue cable, blue hose you may or may not be able to see goes to the same vacuum system. So you've got a vacuum chamber here. Your thing that you want to sputter goes on the little table there. Your target, the metal that you're going to sputter, goes in the top here. There's a DC magnetron that energizes the whole system. You let a little bit of argon in to make the right kind of plasma, and over the course of a few seconds, it'll shoot enough metal onto your target to put a few atom thick layer onto it. So this is useful not only for gold coating ants, but also for if you want to put that metal layer onto your semiconductors. So if you're making semiconductors, you typically will want to you'll build up multiple layers, some of which will be metal, and the best way of putting that on is sputtering. I'm mostly interested in using it for the parts I want to make for a couple of things. One is for titanium nitriding some parts, which gives a very hard surface to them. That's done often with cutting tools. If you go and you buy titanium drill bits from Home Depot, they're probably titanium nitride coated. So you get a very hard surface onto parts, and using a sputter coater, you can do that not only onto metals, but onto pretty much any kind of part. Also for some kind of aesthetic effects, because ultimately I want to make watches and watch parts, and it's surprisingly important in that world that it looks cool. So, we'll make some cool looking parts. Once you've actually made your piece, you typically don't make one transistor on a wafer. You'll make an array of them, usually laid out in a grid, and you've got to get them back apart. So you've got this silicon wafer that's 0.2 millimeters thick, something like that, and you now need to very precisely cut it into pieces. And so this is a dicing saw, and as with most of my equipment, it's from probably late 70s, early 80s, and is meant to hold up to about a 2 to 3 inch wafer. The wafer goes on this little vacuum chuck here. There's a blade, I'm guessing because I can't really see the screen very well, but there's a horizontal saw blade there, which is a very thin diamond-coated disc, an air spindle that spins it up really fast, a microscope so you can see where you're lining up with, and it's got some stepper motors that just move the table back and forth. And so you go through and you program it with these flip switches to do a cut, move over 1/2 centimeter, do another cut, and it'll go through and happily do that cutting for you. So this allows you not only to cut your pieces apart when you're done, but also I'm working with very small wafers. This 1-inch fab idea. It's kind of the scale I'm thinking as well, where most of my stuff is 1 inch, maybe up to 2 inch. When I'm buying surplus wafers, they're often in other sizes. And so being able to cut out squares or whatever shape from those is pretty important. That's kind of the last piece of infrastructure needed around it. If I wanted to actually build electronics, you also need a die bonder, which is where you take this tiny little fragment of silicon with your thing on top of it that you've cut out, and you then stick that to usually a metal substrate. If you think of a transistor that's like the older metal cylinder transistors, the bottom of that is got that piece of silicone stuck to it, and then the rest of it is just a protective cover. And epoxy encapsulated chips, the tiny fragment of silicone is somewhere in there. And then you've got to attach wires to it for the electrical signals to go in and out. And so the wire attachment is done using a wire bonder, where it's a kind of similar looking thing. You've got a microscope to look through, at least the manual ones. You've got a microscope to look through, you've got a little table you move around, and you've got a button to press where this finger comes down and bonds a wire to that spot. And so you go around your chip, you find the pieces that you want to connect to, and you go I want to wire from here to here. And it's a kind of slow, tedious process to do by hand, but if you're just making a handful of transistors, it's not that bad. Generally speaking, I found it to be pretty essential and really important to be able to make some of these parts yourself. I mean, I mentioned that the column is about twice as high as the actual components because of the various adapters and bits and pieces I've had to stick in. It's been pretty key to be able to make some of those myself. This is where, if you don't want to turn your basement into both a fab lab and also a machine shop, this is where getting involved in your local makerspace or place that has a lathe and a mill and will let you use them is really kind of essential. A couple of parts. This one is the bottom of a safety thing that I'll talk about in a second. This is a O-ring encased in a little inner and outer ring to hold the O-ring in place. And these are used really commonly for one of the styles of vacuum fittings. They come in different diameters. There's a few standardized diameters. And what you do is you put one of those between your parts, you clamp them together with enough force to compress the O-ring. When you pump your system down, it gets further clamped because of the vacuum. And that's enough to hold everything together and keep it airtight. These are really nice to work with because all you have to machine is a groove big enough for the metal inner ring to sit in, and then a flat surface for the O-ring to sit on. And so it ends up being a really easy way to build pieces and connect them together. I mentioned mass flow controllers. I'm going to mention them again because I really wish somebody had told me about them like 20 years ago before I spent a lot of time building closed loop systems for gas control. Mass flow controller is a all-in-one system. Gas comes in, gas goes out. You give it 0 to 5 volts, and the 0 to 5 volts controls how much comes in from 0 up to the full range. 1 liter per minute, whatever the range of your mass flow controller is. This is a really simple setup that I put together that just has a potentiometer to control that control voltage and a switch to turn the gas on and off. And you just turn the knob, and based on where the knob is, you get an output. Of course, you can connect them to your Raspberry Pis, Arduinos, BeagleBones, whatever your favorite microcontroller with an analog output is, and drive them from that. There are different kinds of them that operate at different speeds. And they tend to be calibrated with different gases. So you'll see mass flow controllers for nitrogen, for CF4, for hydrogen. They will typically, modulo what the seals are made out of and how corrosive your gas is. They'll usually work with anything, and there's calibration adjustments you can do. I want to almost end by just mentioning a little bit about safety, because this is the dad part of the talk. I apologize. If you're working with flammables, get a flammables cabinet. Keep your fire exits clear. Use a firm fume hood, goggles, gloves, all that. If you check out your local nano or micro fabrication resources, there are a lot of these labs all around the country, usually affiliated with different universities. They pretty much all put all of their standard operating procedures online, and that'll tell you, like, hey, this chemical is super dangerous, make sure to only use it in the fume hood that's rated for it. And they tend to be written in non-hysterical language and to tell you actually reasonable precautions that you probably do really want to take when you're working with this stuff, especially if you're doing it in your garage or your basement and have family members and other humans around where you're working. Also, as you're thinking about processes, I've tried to be really careful to pick processes where all of the gases that I'm using are non-toxic. All the chemicals I'm using are relatively non-toxic. I'm using potassium hydroxide. I'm not using hydrofluoric acid, which you use for a lot of etching processes, because I'm not comfortable having it in the house. Other people make other decisions, and we'll talk about some of those people on the next slide. Have cleanup materials ready, and think about storage and disposal. If you call up your local hazardous waste people, and I'm not saying to use a burner phone, but maybe don't tell them your address, and talk to them, they can be surprisingly helpful. It's saying, well, yeah, you've got a few milliliters of this stuff, just dilute it and put it down the drain, because it's basically Drano. Or they may freak out. And if they freak out, pay attention to that, because they may have good reasons. So a few other resources. First couple have great YouTube channels. Jerry Ellsworth has a bunch of videos about making transistors at home specifically and using really low-tech ways of doing this. It does use hydrofluoric acid for the etching, and she's got some videos about working safely with that, building your own fume hood and trying to do that in the most reasonable way that you can. Hydrofluoric acid is absorbed through the skin, interacts very strongly with calcium, and like a skin exposure equivalent to covering your hand is enough to kill you, and there's really nothing you can do about it. So you want to be careful with it, work with lower concentrations, and just know what you're getting into. For more complicated semiconductors, Sam Zilloff is doing really interesting work around and working toward a full thin film deposition. I think he's trying to build like an Intel 4004 or 8008 at home. So it's really cool stuff. He's got some good videos. For MEMS, there are a bunch of these university programs that have good training videos. One that I like is called Support System for Microsystems Education. And then for vacuum lasers, DIY repair, general snarkiness about home electronics, Sam Goldwasser at repairfact.org has been like my go-to for 20 years plus. Okay, so at this point, I'd like to take any questions, comments. Thank you very much.
Hi.
Hi.
Do you know the name Ishtok Bentov?
No, but I do now.
If he were giving a talk here today, his bio would be almost the same as yours.
Okay.
But he died about 40 years ago, or
Okay.
roughly.
Yeah.
I have a little, like a chapter that I sometimes read at open mics as a short story. But he invented medical devices.
Okay.
Hospitals would go to him and ask, say, we need this, and he would invent them. I actually didn't meet him, but I went to a workshop where his wife was a sculptor. Actually, well, just to cut this short, it seems odd to me, but on YouTube you can find him. If you look for New Heaven, New Earth,
Okay.
it's like an whole hour.
Okay. And if you have a moment at the end, if you can catch me and give me the spelling.
Okay, yes.
Okay, thank you.
Also, his book is Stalking the Wild Pendulum.
Okay, thanks. Okay, other questions, comments? Anybody want to tell me I'm an idiot or this is a terrible idea? I'm sorry? Not really. I've got some parts that I've made that I'm not happy with, and they're kind of crappy, and I'm sorry I don't have better pictures. So it's one of these things where when I proposed the talk, I thought I would be further along in 6 months. So great ambitions, not quite as far as I want to be. Hoping to come back and show more, but there we are.
Do you have any, I guess, entertaining stories? Sorry. Do you have any stories about learning this stuff the hard way?
Yeah. I probably should have mentioned. So this thing on the safety slide is a little piece that I made. The tag is hanging off of a rupture disc. What that does is if your system gets over whatever the pressure is, it ruptures. These are the same things they use on Mythbusters all the time for testing whether you'd be killed by an explosion. You know, they put them in a circle around it, and if the air pressure across it is greater than whatever, then there's a hole in the disc. So they're actually used in industry for pressurized systems and things. I've got it on mine, not because I have a pressurized system, because I've got a vacuum, you know, it's a negative pressure, but because I've got the whole system connected through the mass flow controllers and regulators and valves and whatever to compress gas tanks that, you know, are ultimately at a couple thousand PSI. And I want to avoid turning, well, that's on the end. I want to avoid turning this whole thing into a rocket, you know? And so the entertaining story is that, yeah, I did once blow up my kitchen with a ruptured pressure vessel. And so having emergency venting, or, you know, even if you're never expecting to pressurize the things, is a really good idea. Yeah. I also want to point out, I think this is the only possible slideshow for this setup, or screensaver for this setup. It's the old pipes. And so I was really happy in running Windows 98 to get that back.
Thank you.
Okay. Anything else? Okay, then thank you very much.